Greetings, everyone from Trondheim. Thank you for inviting me for this exciting workshop, and I'm looking forward to hear about your use of AI and applied machine learning to different Arctic challenges. And today I wanted to talk about performance of humans and deep learning algorithm when it comes to operations in extreme environment. As an example of extreme environment, in this talk, we will consider Arctic. Arctic, it's warming up really faster than the rest of the world. And unfortunately, we still have some missing pieces here. And we have often erroneous predictions from our models. We have missing observations. We have undetected events and failures to detect rapid changes on the ground. And by rapid changes, I mean changes that can happen, for example, within hours. For example, ice drift. And from a machine learning and data science perspective, Arctic can be considered as a small data problem. Data very expensive, in situ data very expensive to get, and it's not so many of them as we would like to address our challenges. And at the same time, human presence in the Arctic has also increased substantially over the last decade. Here you can see two maps, and so with the shipping traffic from 2012 and 2021, the data comes from one of the Arctic Council's working group, PAMI. It's a protection of Arctic marine ecosystems from Arctic shipping database. And what you can see here, the white lines on the maps, they show the actual tracks of ships that are greater than 100,000 gross tonnage. That's a huge vessels that could be up to 300 meters long. And not only the size of the vessels that visiting Arctic increases, but also the number of vessels. We see increase of number of vessels operating around Svalbard, especially cruise shipping segment is growing. Also, cruise shipping segment is growing around Greenland, in Canadian waters along the northwest passage. You could see the yellow line. It's a cruise shipping traffic from 2019. Again, data from Arctic ship traffic database. And some estimate when it comes to tourism that in future we will see 8 to 9 million tourists visiting this area annually. And unfortunately, when it comes to technology, we do not have Google Street View for the oceans yet. Maybe in future it will come, but for now we can use this increasing activity as an opportunity to collect more data. Currently, we also have a big challenge. There is a huge gap between the state of the art from automation and what is done in health sector and what is done in commerce to what is actually available for the Arctic users, to those dealing with the scientific problems, those operating in the Arctic, investigating and study Arctic phenomena. We do not have expertise and tools for harsh environment when limited crowd sensing possibilities, and when also Arctic, it's relatively little common knowledge about this area, and we need also domain expertise also limited. Just to demonstrate you some of the state-of-the-art versus ice terminology, I have tried a couple of days back, I tried to search for a growler in one of the search engines, and growler, it's a piece of ice that floating less than 1 meter above the sea surface. And as you could see, when I try to search, the search result doesn't look like a piece of ice at all. It's something else. So when we started this work a couple of years back, we tried to build something useful that Arctic users can also use. You can find more information and more tools in our publications. All of them are open source. We also often publish open source codes. So if you have your own data sets, you're free to use our codes as well. And in this talk, I'm going to focus on comparing the best human and computer performance, looking at the computer and human vision problem. When an expert looks at an ice image, then actually can tell a lot about what ice objects are present, about their shape, but also about sometimes their size, for example, ice concentration. They also can tell about ice age, how old ice is, and sometimes even how thick the ice could it be. And if computers can do the same task too, they can be of great help to navigators. They could be great help for operators in the Arctic, and also to the scientists. They could help with reporting on the ice conditions and at much larger frequencies than currently done. And they can also have a great help in education and training of the next generation ice experts. But can computers do the same as good as human experts? That remains to be seen. So what we have done, we have asked experts, and actually ice expert and Arctic experts look something like that. So we ask experts, and we ask also novices with no prior ice experience or operations in the Arctic to perform a certain ice object classification task. And we compare their performance with the performance of a computer vision algorithm. Both humans and computer, they went through the training phase where they have looked on the images and the ice objects presented, and they had unlimited time, at least when it comes to humans, they had unlimited time to look at the image and to study the ice objects. When we compare the performance on a holistic level, we looked on similarities when it comes to the sensing device and interpreting device between human and computer vision system. And we have not addressed the fundamental differences when it comes to how information is processed directly in the brain when it comes to the neurons. So we only looked at the best performance, meaning that we didn't limit time for the humans to answer the question. So then they can invoke maybe more complex information passing processes in the brain compared to those to the network. So that could be different, but the objective was to compare the best performance from humans and from the algorithm. So both humans and computers in our experiment, they asked to look at their image and select their ice classes appropriate for the current image. For example, in this image, it's brush ice and icebergs that you could see from an ice types. And in addition to wearing just clean images relatively with good visibility, we also try to mimic some of the common Arctic conditions, and we also generated images with distortions that could be met in the Arctic. For example, blur, you could see blur varying from clean to scale 3, 3 being the most difficult brightness, representing lack of daylight, fog, which is also frequent in the Arctic areas, and some noise when it comes to the images collected from the Arctic area. On the left-hand side, you can see results from our experiments. From 3 group on the top, we have results from novices, on the middle experts, and on the bottom you see computers. We have used here to present you F1 score, and the correct fraction, it's a number, it's a percentage or a fraction of the correctly identified objects on an image. And we present it as a function of the distortion level for different distortions: clean, noise, blur, fog, and darkness or brightness. And some things weren't surprising, and it was common that we knew from before, and it was also proven on other objects, but some came as a surprise. Something interesting that on clean images, that network outperforms our human novices. And also experts surprisingly didn't perform that well as we did expect. And one of our explanations is that that there could be a lot of disagreements between the definitions and objects among the experts based on their operational experience compared to what we have defined to being the ground truth. And that could constitute to the difference in scores obtained. And in general, human participants, they have distortions better than networks, especially the blur and noise that we kind of have been shown from before. But computer models are better, for example, in handling brightness and fog, and this is something comes from their training, since often we introduce images with different brightness as a part of the training set, so they are superior than our human participants. And also as a feedback for our kind of experiments with the testing, we got a feedback from our users is that the testing system and the training system that we have developed, it's actually also a great tool that can be used for training and testing ice experts to classify different ice objects and to training them for the future, in future educational systems. Currently, we are extending our work to also not only classification, but segmentation tasks and extracting additional parameters from an image, for example, ice concentration and ice drift, and comparing those with the human performance as well. We are looking into building weather-independent solutions when it comes to the raindrops, snow, and also testing our segmentation models in the field. Also, one of our activities is that we are integrating models or from prediction models, regional, local observations, and all the way up to the satellite observations in one infrastructure as a part of a larger project. And having that been said, AI and in general had a lot of potential in the Arctic, and I hope in future we will see more AI experts joining this field and helping Arctic societies and addressing Arctic needs from a machine learning and data science perspective. Thank you.
Yes, thank you very much for inviting me. As it was said, my name is Konstantin Maslov. I'm a doctoral candidate at the University of Twente, and I'm going to present some results from the massive project towards fully automated glacier mapping in the Arctic regions with deep learning. So first, I will shortly introduce the overall idea of the project, the knowledge needs, and the research objective. Then I will cover some case studies that we conducted with the main focus on mapping the Arctic. And I also would like to share some of the results from the Alps. And I will share our next plans and conclusions. So as we all know, glaciers are an essential part of the climate ecological systems. They directly related to climate change because they're good predictors of climate change. They're related to sea level rise, to the availability of water resources in the terms of its amount and quality. They also affect the ecosystems, and they also, the glacier shrinkage increases the frequency of hazardous events such as glacial lake outburst floods. So we know that glaciers are changing, and it's especially true for the Arctic because of the Arctic amplification. And of course, we would like to estimate in the sense this process better in order to make better predictions and in order to better quantify what's going on. Therefore, there is a need for multi-temporal large-scale glacier inventories and glacier mass balance datasets. It's better if it has a higher temporal resolution as well. But unfortunately, such inventories and datasets are missing. The biggest inventory for glaciers that we have is GLIMS. but it doesn't cover all the areas with high temporal resolution. And sometimes we have a lot of missing data in it as well. So the overarching goal of the massive research project is to produce large-scale inventories, including detailed glacier maps and surface mass balance time series. And at this stage, we are focusing on global scale mapping. And to achieve it, we are developing fully automated methods for glacier mapping based on deep learning. So for the Arctic, we selected 8 areas of interest based on the data availability of the reference data in GLIMS and other inventories that we could access. And every area of interest was divided in squared tiles, and we selected some tiles for training the model, some tiles for validation, and the rest for testing. In this case, for input data, we use multi-source data. It's a mix of different optical platforms. For example, for Alaska, we used mainly Landsat 5 data. For Greenland, it was Landsat 7. For Spitsbergen, it was Sentinel-2. And for Scandinavia, it was Landsat 8 data. It's also very diverse in terms of what kind of digital elevation models we used. We used ELOS World 3D. For Greenland, we used specific DEM produced based on Esther and Spot 5 acquisitions. For Spitsbergen, we used digital elevation model from Norwegian Polar Institute. And for Scandinavia, it was Copernicus DEM. And as I mentioned, for reference data, we also use different sources. It's mainly GLIMS, but for Spitsbergen, we used unpublished inventory from NPI. And because we have multi-source data, first is multi-source because of different platforms for optical data, and second is multi-source because of different types of data that we use. It's optical imagery and it's digital elevation models. We train models with in-network fusion of these types of data. So in this slide, you can see the results that we obtained. In general, the model performance is great, except some particular cases, which I'll cover later. Yes, we see that for almost all the metrics, all the most regions, we have very high values of precision. Recall, Scandinavia is a bit less, but there is a reason for it. And we claim that further fine-tuning of the models to a specific region could potentially improve the situation, but it's something to be investigated. Now I'll go to the classification results. And well, it's not so challenging to classify clean snow and clean ice, and you can do it even with simple band ratio methods. So we can see that our network very well grasps all these bright features. At the same time, we see nice performance on debris covered ice, on Calvin fronts, and especially on shadowed areas of glaciers, which sometimes are difficult to classify. And what else is nice with this approach is when you use band ratio methods, usually you try to adjust it for different regions, for different acquisitions differently. In this case, we use one data set, one model that can do it automatically. Here I would like to show some very interesting specific examples of what we obtained. First of all, as I mentioned, it's debris covered ice. So we have very dirty ice, which is spectrally very similar to the surrounding rocks. And the performance of the network is very nice. Partly it's true because of the Alaska and glaciers, debris covered glaciers have very distinctive textural features. What is also surprisingly nice is how well our model grasps the idea of vegetation covered ice in Alaska as well. Of course, the results are far from ideal, but we didn't expect that it would perform so well based just on optical and DEM data without using SAR acquisitions or thermal data. It's also robust to different type of artifacts in imagery. For example, here we have a tile with a Landsat 5 artifacts close to the scene boundaries, and it doesn't affect the performance of the model. And we also can see that predictions for Calvin fronts are even better than ground truth. So we used these entries from GLIMS, which are not ideal, and we used not ideal entries as well for training. So we were very skeptical for if it can nicely classify Calvin fronts, but in the end it can. But of course, it's not ideal and there are mistakes. And one of the main problems is predictions for small ice or snow chunks are not consistent. And well, the state whether these ice or snow bodies are glaciers actually is quite questionable. So in different inventories, different authors relate them to different scenes. For example, we have this inventory for Scandinavia where very small snow chunks are classified by authors as glaciers. At the same time, for Greenland, we have quite a different situation when all these small chunks are not included in the inventory, and our model was confused in the end what to consider a glacier and not to consider glacier when we are talking about small bodies. So yes, there is a type of inconsistency, and probably it can be solved later by some post-processing and introducing very specific limitations of what to consider glaciers. And also some dirty glacier tongues are still problematic to classify, as we can see here. In general, it can restore the overall shape of glacier tongues covered with rocks, but it tends to overclassify it, to overestimate its area. What we can do with it, our motivation is, our idea is that we can still solve this problem by spending more time on methodology, by using more complicated models, or maybe introducing thermal channel to classification, or SAR acquisitions as well. So we did a kind of similar case study for the European Alps. In that case, it was just a region scale mapping. We used the Sentinel imagery, including Sentinel-1 and Copernicus DM, and ground truth data was inventory by Paul Frank. What we did here, we also compared the fully convolutional networks with some baseline methods, such as random forest. And we also investigated how adding different features to classification helps to improve the situation. Well, in general, we see that fully convolutional models are better, and adding more features for classification increases the performance. And it's especially true for glacier tongues. Here you can see some close-ups from the test tiles, the original RGB imagery, the ground truth data, and also 3 columns for random forest results with 3 different sets of features, and 3 columns for deep learning models with 3 different sets of features. And we can see that performance increases going from random forest to a UNet-based model, and also from going from just optical to optical plus DM plus SAR data. And it's especially true for glacier tongues, as I mentioned already. So what we are planning to do next in our research project is to expand our data sets. And we collected quite some data for different regions to make it as much diverse as possible. And we also expect that adding new data in different regions can allow us to get better representations and better knowledge inside our models of what glaciers are in general. And for example, adding data for one region can also improve classification results for other regions. And in terms of coverage, you can see some statistics here. We covered almost all the Central Europe, New Zealand, quite a big chunks of ice in southern ends, Alaska, Spitsbergen, and Scandinavia, less in how mountain Asia, Antarctic, and Greenland. And we didn't include any entries from Western Canada and USA, from Arctic Canada and Russian Arctic, because we expect that probably other glaciers from other regions is enough to get nice results. So in a nutshell, our experiments have shown a decent performance of fully convolutional models for 2 case studies. One is mapping glaciers in the Arctic regions. The second one is mapping glaciers in the European Alps with the in-network fusion of different sources of data. We also know that utilizing more data sources, for example, Svalbard scattering and interferometric SAR, considerably increases the performance. And we hope that further extending the datasets will increase the performance of the models and make fully automated glacier outlines mapping feasible on global scale. And in the end, in our project, we are aimed to producing inventories, which in the end will facilitate research in different areas of science, such as climatology, glacier modeling, and others. And if you'd like to see more information about project, massive project, you can go to this QR. And if you would like to contact, for example, me later, you can use this email. So thank you for your attention. I'm happy to hear your questions.
Hello, everyone. Today, I'm going to introduce the Arctic research ongoing at ASU and within my research group in applying machine learning and AI for Arctic permafrost mapping. So why mapping Arctic permafrost is an important problem? Because permafrost, which is also known as the permanent frozen ground, covers 15% of the land in the Northern Hemisphere, and nearly 4 million people live on top of it. As the global temperature increases, the frozen ground started to thaw, and this has caused significant local and global impacts. For instance, the thawing permafrost results in increased coastal erosions, and this negatively affecting the Arctic ecosystems. And the permafrost thaw has also put at least half of the Arctic infrastructure in danger, causing a lot of the damages to the buildings, roads, and oil pipelines. And as the frozen ground becomes unfrozen, a large amount of greenhouse gases are being released, and this further accelerates the rates of global warming. So we need to develop a solution to map the Arctic permafrost and their thawing stages so that we can gain a better understanding about the permafrost dynamics and its linkage to Arctic warming. So why do we need machine learning and AI? As we possibly agree, we are in the era of big data. There are huge amounts of Earth observation data available to help us understand the changing environment. For instance, the satellite company Maxar Technologies have collected 125 petabytes of global imagery in its archive. To make the best possible use of this data to enable data-driven discovery, we need to apply the more advanced methods and tools. And this is where AI and machine learning comes into play. In recent years, AI has received a lot of attention and breakthrough development, especially in the areas of deep learning. And in image analysis, deep learning models have shown outstanding performance. Its applications can be categorized into 3 broad classes. Image classification is the simplest one. It just needs to predict what is inside of an image. And object detection goes one step further. Besides predicting what's inside, it also requires a model to predict the bounding box locations of each of these features. So here I just draw a few of the bounding boxes to give you an example. And instance segmentation is the hardest one. Besides predicting what's inside, it also requires the model to delineate the exact boundary of each feature. And the work that I introduced here belongs to the 3rd category. In terms of using AI to support automated mapping of permafrost features, we have seen a number of exciting research. And for example, the one on the left-hand side shows the architecture of MAPLE, mapping applications for Arctic permafrost land environment. it uses a popular instance segmentation model called mask-RCNN to achieve the pan-Arctic level mapping of ice wedge polygons. And another interesting work is conducted by researchers at University of Colorado. So they are using a semantic segmentation model called the Deep Lab to map the salt slumps in the Arctic. This is another important permafrost feature type. So what is urgently needed now to understand the permafrost dynamics is to gain the real-time mapping capabilities at pan-Arctic scale. Because for one, our analysis is often behind what is going on in the Arctic. So real-time mapping will be very valuable to examine the changes as soon as observation data becomes available. Second, the regions of the permafrost covers is very big. So this figure shows the over 5 million square kilometers of the tundra area within Alaska, Canada, and Russia. And in the MAPLE framework and also in our research, we are using very high resolution, like half-meter resolution maxar imagery with multi-spectral bands to making the Arctic permafrost mapping. And to cover the entire study areas, there needs 25,000 of satellite image, and this is total of 180 terabytes of data. And to prepare the AI-ready dataset, each of this image needs to be further partitioned into 40,000 image tiles. So if we time 25,000 by 40,000, that is a total of 100 million image tiles to be fed into the AI model for it to learn and make predictions. So this is definitely a big data problem. So to address this issue, here I introduce our recent work in developing real-time AI for Arctic permafrost mapping. And this work uses a state-of-the-art model called the sparse instance to achieve real-time processing. The advantage of this model is that it can yield comparable detection accuracy to the current popular segmentation models, such as mask-RCNN, but at a much faster speed. And it achieved this by introducing a few new learning strategies. So one strategy is called the single-level prediction for faster inference, because natural features tend to have a large variation in their size. So most methods adopt a multi-scale feature fusions and also multi-level predictions. So just like the one on the left-hand side, once given an image, so the multi-scale features will be extracted. And then the prediction will be built upon each of these individual feature maps at different scales. So this step will take substantial time. And sparse instance is able to accelerate this processing by enabling single-level prediction. So as you can see in the feature extraction pipeline, it still extracts features at multiple scales. But these different feature maps are sent to the encoder to fuse that into a single level feature map with multi-scale representations. So this, and then this single feature map is sent to the decoder for further prediction. And another strategy to help the model to achieve real-time inference is a generation of instance activation map. And in other models, to locate where an object is, the model usually needs to draw a lot of the candidate bounding boxes, sometimes up to several thousand. And then through post-processing, these bounding boxes are being ranked, and the best model and the best bounding box will be found. And this step takes a lot of time. And in sparse instance, instead of exhausting every possible object locations, it first creates an instance segmentation map to highlight the important image areas. So the model will be more informed in terms of where to draw the prediction. So this way, it will accelerate the processing and making good predictions at the same time. So here, we apply the sparse instance model to map the ice wedge polygons using the half-meter resolution maxar imagery. And to evaluate the performance, we compare the model results between the sparse instance with a very popular segmentation model called the mask RCNN, and their performance in terms of prediction speed and also prediction accuracy measured by average precision are compared. So as we can see from this result, sparse instance can not only achieve better detection accuracy, it can run at a speed nearly twice as fast as mask RCNN. So this shows that this model really achieves very good performance in terms of both measures. And we also draw a trade-off curve between accuracy and speed. So for a model to be considered as achieving real-time performance, its inference speed needs to be faster than 30 FPS. And the mask RCNN is here, so it's not yet real-time. And we also run the sparse instance model with different configurations to, in the hope to further push up the speed. But as you see, as the speed increases, we have to sacrifice some of the accuracy. So this is always a trade-off between accuracy and also speed. And here shows the segmentation results. So this image shows the S-wedge polygons with their ground truth labels. So these are all high-centered S-wedge polygons. And the right hand shows the prediction result by the model. So visually, we can see the model makes relatively good predictions, which are consistent with the human labels. But we can also observe some discrepancy, like this one. The model predicted as one big objects, while in the human labels, it was labeled as 3 smaller S-wedge polygons. And there are also cases where the model fails to predict the existence of a feature. And this is another image showing all of the low-centered S-wedge polygons. Again, the left-hand figure shows the ground truth, and the right-hand figure shows the prediction. So as we can see, most of the S-wedge polygons were delineated pretty well, but we also observed a few failing cases. So here, I introduced some of our ongoing research with preliminary results. So in our current work, we didn't separate different types of S-wedge polygons. And in the future, we are going to extend this detection network to be able to categorize different types of S-wedge polygon because they are important indicators of the thawing stage of permafrost. And we're also going to include the detection of different types of permafrost features, like to include the detection for salt slumps and also pingles. And we're also developing strategies to further improve the model to achieve both better detection accuracy and also the inference speed. And once we have the data set ready, we will be able to better link the permafrost dynamics with Arctic warming to hopefully predict what is going to change in the Arctic region in the near future. And another project that we are about to start is to provide AI training to current and the next generation Arctic scientists. And we call this project Cyber 2A. And this project aims to achieve 3 objectives. First, we will establish and expand an Arctic AI research network. And then we will also deliver a number of training activities in terms of both in-person workshops and also online learning modules. And our ultimate goal is to create a sustainable and scalable learning communities. So we will kick off this project in March 2023. If you are interested in collaborating on this project, please feel free to reach out, because to enhance Arctic researchers' skills in AI, it is definitely needs community efforts. Thank you for your attention.